Okay, so after learning probability of a macro state, let's try to understand the maximum probability, or the combination for which we would have for the macro state whose probability will be the most, okay, or the maximum probability. So as you can see that, as I discussed, a macro state will have higher probability, okay, if it has got more number of microstates. So the microstate is the number of microstates for a given macrostate decides what its probability will be. So now for the general case, so we are considering the system which have got two compartments of equal size, okay. So in that case, and we have also seen in the earlier example, is that the total number of microstate for the system is, we know that this is 2 to the power n, okay. So this is total number of microstates, okay. So that's equal to, okay, 2 to the power n. So now we need to find out for a for which combination of which distribution, or like, for where the number of microstates will be maximum, okay. Now we know also, see, this number of microstate is given by, so this particular thing is given by, as we all know that if you have n number of particles, so and r number of particles are in compartment A, and in B there are n minus r number of particles. So in that case, total number of microstates given by so NCR, okay. So from earlier studies or from the elementary algebra, we know that, so that this NCR, this value will be maximum, it will be maximum, so it will be maximum, okay, for the if this r is equal to n by 2, right. And imagine now this n, because n is, in reality n is going to be a very large number, let's say n is an even number, okay. So so this, as you all know, this probability of the macrostate is given by the ratio of number of microstate to the total number of microstates, and here total number of microstate for any given system, or for that system that we have considered, is constant, that is 2 to the power n. So for that system, that macrostate will have maximum probability which has got more number of microstates, and that case happens if it is r is equal to n by 2. So the probability max we can think about, let me just move this little bit up, okay. So we can have, so the probability, so the maximum probability that we can have is so if it is NC n by 2, and this is divided by 2 to the power n, okay. So if we go ahead with our whatever we have done, like the algebra, so this is r is n by 2 factorial, and this is again n minus n by 2 half factorial, and then given to the power n, okay. So this will be your maximum probability, okay. So we can obtain the maximum probability is for this combination, okay, where this r is n by 2 and it is given by this particular formula. So you can I can draw a box around just to highlight the stuff, okay. Now similarly, we can have the minimum probability for the combination which will carry the minimum probability. In that case, so ultimately this maximum, minimum, or the probability is decided by this NCR factor, right, because the denominator is constant, 2 to the power n. So we know that to have minimum value for this NCR, so we need to have, if r is equal to 0, then we will have this value to be minimum, this NCR value to be minimum, or we must have r equal to n. So these are the two cases. So we can have the probability minimum will be, it is n c, so r is 0. In that case, let's say first case, let's assume, so let's assume r equal to case, so given by the denominator is 2 to the power n. So in that case it will be n factorial divided by 0 factorial n factorial to the power. So ultimately it will be 1 by 2 to the power n. Okay. So again, for the case where if r is equal to n, in that case also, if you carry out the algebra, n c r is n, then 2 to the power n, n c n is 1. Okay, we need not calculate, I guess. So again it will be 2 to the power 1. So the minimum probability we will obtain 1 by 2 to the power n. Okay, and the maximum probability that we have got in the earlier case. Okay, so now let's try to look at one example. Okay, so here when to calculate the probability that in a tossing a coin 5 times. Okay, so I am tossing a coin 5 times. Okay, so we get 3 heads and 2 tails. So these 5 coins, let's say coin number 1, 2, sorry, so I am doing what, 3, 4, 5, let's say. Okay, so I am tossing a single coin 5 times is equivalent to tossing 5 similar coins at a time. Okay, ultimately result will be same. Okay, so this is equivalent. So tossing a single coin 5 times one after the other, completely independent events. Okay, so result is random. Whereas and take same coin or similar coin 5 and toss them up at the same time. Okay, so now so we need to find out the probability that there will be 3 heads and 2 tails. Okay, so now macro state is what, 3, 2. So where the first one represents head, okay, second one represents tail. So what is the probability of finding that? So here see this the example that we have considered, this distribution of particle within a box having 2 equal compartments. Okay, it is similar. Okay, the conceptualize, if you think about it, it's similar to toss it's equivalent to a tossing of a single coin, meaning it has got equal a priori probability, and if you think about a particle going into any one of this compartment is half the probability of entering into any one the half. Similarly in coin toss also, there are only 2 outcomes, so the probability of getting 1 is half. Okay, so we can think about, so now we need to calculate the probability. Okay, probability of that macro state, sorry, that probability of that macro state, which is 3 by 2. Okay, so now first we need to calculate the number of microstates for this. Basically we need to calculate W. Okay, this. So we know to total there are 5. So the number of microstates for this given macrostate will be NCR. R is here 3. So I will get 5 factorial by 3 factorial by 2 factorial. So in that case, so what I will get, 4 into 5 divided by 2, so it will be 10. Okay, so the number of microstates for this given macrostate is 10. So 10, and then 2 to the power n, so here 2 to the power 5. So it will be ultimately, so 5 by, so I can think about 2, I take it out, so 5 by 2 to the power 4, which is 16. So the probability of occurrence of this macrostate, which is 3 heads and 2 tails, is 5 by 16. Okay, so let's go ahead and see some more. Let us learn some more on this macrostate and microstates. Now consider the 3 particles in two compartments. In fact, whilst trying to learn this macrostate and microstate, I have started the example of 3 particles in two compartments, okay, two equal compartments in this case. And now see, let's try to understand what things will change if we have distinguishable particle and indistinguishable particle, okay. So let's say first talk about distinguishable particle, which we have already discussed. Let's say A, B, C are my three particles and trying to distribute in two equal size compartments, and we all know there is number 3, meaning the 3 total number of particles. So since I have two compartments equal size to which I need to distribute these two, so n is 3, so n plus 1 will give me the total number of macrostate that I will have for this system. So I know n 3 plus 1 is 4, so 4 number of macrostates I got here, okay, 4 total. And what will be those? So if I look inside, so ABC, so all this combination we have come across already. Okay, 2 1, this has got 3 microstates, similarly 1 2 3, and whereas in the 3 0 and 0 3 we have 1 microstate each. Okay, now this is possible if we have these particles are distinguishable, meaning I can identify these particles to be A, B, C, okay, or I can name them, I can distinguish one particle from the other. Now what if these particles are indistinguishable, okay? So let's say the best way to name them is all of them are same, alike, okay? So like A. So how I have named it, all these particles, so they are indistinguishable, so all are A's. So in that case, if you compare the macrostates, so see, number of macrostates will be same, right? 0 3 also. So from the macroscopically system will look same. Okay, if you the macrostate will be 0 3 2 1 2 number 2 2. If you see 2 in compartment 1, 1 in compartment B. Okay, similarly 1 2 0 3. However, if I look deep inside, or the microscopic arrangement of the particles within the compartment, if we look at, then I see that the whatever you had for this 2 1 macrostate, you had 3 meaningful different combinations or the ways to get the 2 1 combination, okay. Whereas once the particles became indistinguishable, I mean A all became same. See, I can have only one state corresponding to the macrostate 2 1, meaning all the other combination, whatever, if you exchange the particle, I mean you cannot distinguish from the one state to the other. Basically we have only one microstate, okay. Similarly for the 1 2 also case, anyway we had only 1 1 for 3 0 0 3. See, moment the particles became indistinguishable, there is a reduction in the number of microstates for few macrostates, and of course if that reduces, then the total number of microstate for the system also decreases. So these things we have to keep in mind when we have indistinguishable particles, okay. So then let's talk about the constraints of the system. So constraints of the system means these are restrictions which needs to be these are some restrictions which needs to be obeyed by the system. For examples, where we have considered our system meaning having two compartments of equal size and distribution of particles, in that case, if there are n1 particles in compartment A and n2 are compartment B, and this must add up to give you the total number of particles. So this is like a restriction. Okay, so these restrictions are the constraints of the systems. Okay, so these are conditions where the system has to follow. Okay, so there could be restrictions like, you know, while distributing this many 3 particles into compartments, I may have constraints that the compartments must contain at least one of the particle. So no compartment can be blank or empty. So in that case, if that's the case, then what happens? This macrostate 3 0 and 0 3, this will not be possible for the system. Okay, so only possible macrostate for the system will be this 2 1 and 1 2. So that brings to me the things, the accessible states. So with the restriction or the condition that no compartment can be empty, in that sense the 3 0 and 0 3 macrostates become non-accessible or inaccessible. Okay, whereas this 2 1 and 1, 2, these are becomes accessible states. So under the restriction or constraints of the system, these accessible states are those states which can be accessed by the system, whereas inaccessible states are those states of the system which are not accessible by the system under the given constraints. Okay, so now now this can be broadly discussed. Okay, we will see as you go along the course. You will see some of the accessible states, some of the inaccessible states and constraints of the system. We'll discuss in detail. Now then in static and dynamic system, so like let's talk about our system, this the tossing of a coin. Okay, so when I do toss the coin, if it falls, let's say, head, without any external disturbances or external force, it's not going to change. It's very unlikely, or it's not going to change. If it remains head, it will remain on head. Okay, so this kind of systems where the constituent of the systems, they do not move, or they do not change their position, or they change their state, these are known as static systems. Now whereas if you think about a system, let's say your gas molecules, okay, gas molecules, and being again placed in let's say there are so many thousands or millions of gas molecules are placed in two compartments, and they are this membrane, you can think of it like a semi-permeable membrane. Okay, semi-permeable membrane, permeable membrane you can think about. Okay, now these gas molecules will undergo collisions. So some of the particles may gain extra kinetic energy, some may lose in that process. So it may, these gas molecules among themselves, some of them may get extra energy to go across the membrane, and if it goes, then it changes the microstate of the system. So this kind of systems where the constituent of the system continuously move or change their position move from the one compartment to the other compartment, then these kind of systems are known as dynamic system. Basically what in static systems, once the one microstate is attained by the system, it will remain there forever without any external forces. Whereas in dynamic system, continuously system will try to evolve and try to explore different microstates of the system. So that's what is the difference between dynamic system and static system. Now having learnt about the static and dynamic systems, and we have seen that in dynamic system what happens, the system tries to explore different microstates. Okay, and we know from the principle of equal a priori probability that every microstate is equally probable. Okay. So combining all these thoughts, okay, all the learnings that we had till point, let's try to understand the most probable state, okay, or which we know that's going to be the equilibrium state. So now the most probable state, as you can understand from way it has been given here, the macrostate which has the maximum probability of occurrence. Okay, and from the P max values already we have seen from the earlier slides that P max, so we have calculated event for which combination will have this maximum probability of occurrence. Okay, so we have seen that if there are total number of n particles to be distributed in two compartments, we have seen that if it is, so it will have maximum probability if you have NCR where the R is n by 2 and divided by the 2 to the power n, the total number of microstates. Okay, and this we further, so like in one compartment we have n1 particle, in other we have n2, let's say n1 in particle in compartment A, n2 in compartment B, and the total number is n. And here so this P max will maximum if n1 is equal to this n by 2 and n2 is also equal to n by 2, which is of course will be. So this we already know from the earlier slides. Okay, So P max is given by this. Okay, so in static system what happens, so once the microstate is sort of achieved by the system, and that it will remain, okay, it will remain as it is, okay, it will remain static. But whereas in dynamic system, as we have talked about, okay, dynamic system, what will happen, system will try to explore different microstates and then different macrostates. Okay, so if we can find out the macro state which has got maximum probability of occurrence, that means which will have maximum like higher number of microstates, isn't it? So the P max will be maximum if your because the total number of microstate is same. So this is like proportional to, you can think about the number of like, you know, what should I call it, maximum number of microstates. Okay, so the macrostate which has got more number of microstates, that macrostate will be most probable. And since if you think about the gas molecules or the system of having a gas molecules or other atomic systems, to think about this number of particles is very large. So practically what we will see, that the system will be present or will likely to be in like most of the time it will be in this most probable state, and which is known as equilibrium state. Okay, so like after exploring like different microstates of a system realizes that this macrostate has got maximum number of microstates, and it's more often than not you will find this system to be present in this this state. Okay, so these things will be clear even more slowly when I talk about, you know, many other things as we go along the course. Okay, so let's try to stop here, and we'll continue discussing statistical mechanics and various interesting facts about statistical mechanics, and some various basic concepts will lead to many other interesting phenomena associated with the statistical mechanics. Okay, we'll stop here.